functions. You guys understand we do the inside parentheses, then we do the outside parentheses when there's parentheses nested inside each other. Okay? So I guess what I want to do here is show you how this works. All right, so let's do a little bit of, again, it's some algebra, but we're going to try and put this definition to work here. So we need to check two things. We need to check that f of f negative 1 of x equals x, and we need to check that f negative 1 of f of x equals x. Both things have to be true for me to say that I actually have an inverse. Okay? So f has an inverse if these things are true. And like I said, sections 1 and 2 are really algebra sections. And on the homework for tonight, you're going to do something like this. It says, show that these two functions are inverses of each other. So let me take number 23. 23 says, hey, let's look at f of x is x cubed plus 6. And let's look at g of x is the cube root of x minus 6. We want to show that those are inverses of each other. And so the test is right here. We need to do f of f negative 1, and we need to do f negative 1 of f. So here I go. F of f negative 1 of x. Okay? What that means is everywhere that, see, I'm going to look at the outside function here, f. What I'm really finding f of, oh, and by the way, yeah, they call this guy g. So instead of, to show that they are inverses, what, boy, that's not the best start. Let me try this again, guys. Okay. What I want to do is I want to analyze f of g of x. Okay, that's really what I want to do. I don't know that this is an inverse yet. I want to show that it is. So I'm going to do f of g of x. F of x is x cubed plus 6. G of x is this crazy thing. So what I'm really doing is finding f of cube root of x minus 6. And what that means is everywhere it used to say x, I want to write cube root of x minus 6. Okay? We were going to take x cubed plus 6, but now what we're going to do is we're going to take something else cubed plus 6. What's the something else? You put in cube root of x minus 6. All right? And what happens when you cube a cube root?
It vanishes.
Yeah. So what are we left with? We're left with x minus 6 plus the 6 from above, so we really do get x. F of g of x is equal to x. And so now your job is to try and show that g of f of x also equals x. So let's see what that would be. Well, it's g of x cubed plus 6 this time, right? That's the input. And I have an expression for g. And so what I'm saying is, everywhere that it used to say x, I'm going to put this guy. So x cubed plus 6 goes in place of the x in the formula for g. And now the 6's drop out, so I get the cube root of x cubed, which is x. So if you check both of those, and if you get x each time, you know you have a function and its inverse. All right. And by the way, here's one of my favorite examples. This is not in the book, I don't think. Let's take f of x equals x squared. What do you think I'm going to take for g of x? What do you think? Square root of x. Does that make sense to you guys?
Yes, it makes sense.
So now what do I do next? Try something like f of what? Right. I mean, we want f of g of x, right? Something like that. So what do? We're really finding f of the square root of x. And so like you said, that's the square root of x squared. And what is that? X. So that seemed to work. And now if I take g of f of x, I'm taking g of what? X squared. And so that is, we know g of x is the square root of x. So what we're doing here is the square root of what? X squared. And what is that? X. But there's a problem here. We have a slight problem. And if all you do is just look at the algebra here, you're not going to see the problem. I have to go back to the definition I had on the screen earlier. It says we need f of f negative 1 of x to equal x, there it is, for all x in the domain of the inverse, and for all x in the domain of f. Now domain, what does that mean again? Domain is the set of possible, are we talking inputs or outputs? Inputs. Domain is the set of possible inputs of a function. So hold on a second. See, all these problems up here, I didn't say anything about the domain because the domain was all real numbers. But when we get down to here, okay, actually, I guess my problem is going to be really there. Because what is the domain of this function?
0 to
The domain of g is only from 0 to infinity. Is that true? Can't you put negative numbers in there? Well, we're trying to keep it real, right? So we're going to have real answers. So you can't, I always say that, right? So if I say that this is my domain, okay, then I need this to be true for all the x's in the domain. So the way to see you have a problem, maybe it's easiest to see if you look at the graph. If we graph y equals x squared, we know that's a parabola. But if I give you a particular output, the problem is that there's more than one input that can give you that output, right? Like if I say 9, what's the input? What would you tell me? You might say 3, or you might say negative 3. See, the domain of f is from negative infinity to infinity, so, for example, if I were to compute g of f of negative 3, well, can I do that? Let's see. G of negative 3 squared. So that's g of 9. So that's the square root of 9. So that's what? 3. But I guess what the issue is that I got 3 as an output and I got negative 3 as an input. So I got negative x and x. You guys see that? G of x squared. When you take the square root of x squared, maybe let's see if this rule comes back to mind looking at this example. When you take the square root of x squared, the algebra rule was, do you remember this rule? You had to put a plus or a minus. That's the problem. So I guess my point here is that something like x squared doesn't have an inverse because it doesn't meet what's called the horizontal line test. It's not what we call a one-to-one function. Okay? Not one-to-one. Doesn't meet horizontal line test. Okay. So all that background is kind of something I wanted before I start talking about logarithms. And I thought that's touchy, because if I say what's the inverse of x cubed, you guys are okay with cube root of x. But what's the inverse of x squared? Well, we don't really have one because it's not one-to-one, even though everything else seems to work okay. All right. So, what kind of functions have we been studying? We've been studying exponential functions. What do they look like? F of x equals, I've been using the letter B, which stands for what? That's the base. And then what do I do next? To the x power, right? We put an x up in the exponent. That's called an exponential function. What does the graph look like? Tell me something you know about it. Yes, it's either exponential growth or exponential decay. So it has an asymptote. Let me draw growth for the example. Then it'll have an asymptote on this side, right? And then it also always has to go through what point?
0, 1.
Okay. We know it's going to go through 0, 1 right here. And then it's going to take off. Right? And yes, that's what we called exponential growth. I mean, really take off. Is this function ever equal to 0? No, and it'll never be negative either. But there's an observation I hadn't made last week that I want to make now. Notice this function is 1-to-1. What do I mean by that? It meets the horizontal line test. Do you guys understand what I mean by that? Means if I draw a horizontal line anywhere, how many places will it hit the function at most?
1.
You guys with me? So what does that mean? This implies that f of x has an inverse function. You're not going to run into the problem you ran into with x squared. Each input has an output, and only one input has an output, so you can go backwards. Okay? And what I'm going to say is we call the inverse function a logarithm. And so you guys will see we're going to write it this way. F inverse of x is log of x, but you want to say what it's the inverse of. Okay? So what I'm going to do is I'm going to put the little base down here. Log base b of x. And that could be any number you want. It's whatever number you would have had in the exponential function. One last thing maybe to say is when the base b is equal to e, we say we have a natural log. And you guys have heard of that before, right? The natural log? Okay. All that means is, so if I write ln of x, just think Disney. It's just log base e natural log.
Okay.
Natural log. That's all it is. All right? So it's base e. And base e is what we're going to use the most, because if you look at Gina's question today, the problem she had was when it's not the natural log. Right? But we're going to correct for that today, too. Okay? But I think you guys have done this stuff before. I just feel like there's a lot behind it, and it's worth a reminder here or there. Okay? One last thing maybe to review. There's something called the log laws. You guys remember this? No? Good reviewing? Yes? Okay. We'll review them. So, for example, if I write, something like this. The log of A, B. Say I have a product. Do you know how I can rewrite that? Matt?
Log A plus log B.
That's right. That's right. A product can be written as a sum of two different logarithms. Matter of fact, that's log law number one. Once I write that, you guys are all going to be able to kind of fill in the blank on this one. Go ahead and write down what you think that equals, and you're going to be right. Isn't that nice? The log of A, what am I going to write? Minus the log of B. That's right.
How do you write log of a number as an exponent?
Oh, you're saying if I have a different base.
Well, no, even with that one. So what is, if you want to write log, it's base 10.
Yeah, these are base 10 if we don't write anything.
Yeah, log base 10 of A. How do you rewrite that? There used to be like some loop swoop thing to make it an exponent. I forget how to do it though.
Oh yeah, the change of base formula. I could show you that.
Okay.
But let me do what I think is the most important log law. And that is if you have the log of, I don't know, some number, let's say n, to a power, n to the p power. What happens is you can take that exponent and bring it out front. And so you get p times the log of n. These are the log laws that I'm sure you learned in some pre-calc class or college algebra class. Those are going to come into play. We'll see if that is what you're talking about or something different. So, for example,
I think it's both.
if I take, this is problem 33 on the homework. Well, let me do 32. 32 says we have the natural log of the cube root of 11. Okay? And maybe I want to rewrite that. Well, I guess what I would point out is that you can rewrite it, first of all, as the natural log of 11 to what power? The 1/3 power. And now using log law 3, that's going to be 1/3 the natural log of 11. Okay, there's the power coming out front, as I mentioned earlier. 1/3 kind of comes out front. And so we could check that on the calculator at this point. I mean, I type in, well, a couple ways I could do it, right? I could type in natural log of 11 caret, and then I guess I need 1/3 in parentheses. Okay. Or I could say 1 divided by 3 times the natural log of 11, and those should be the same. Right? According to these log laws. Is that what you were asking about? No. I think maybe you're saying, how do you change bases? Like if you have a different base?
Yeah, I think that's what the answer is. Like it's like log base.
So if I have log base 3,
Sure.
number 33 says that.
Okay.
Log base 3 of 4 square root of 3 over 9. Oh, okay, I have my calculator in the way, but let me show you that. Right? I mean, you can't even type that in the calculator. Because, well, it's base 3. And on the calculator, I have 2 bases I have buttons for. The natural log is base E. And what about the log, just log? You guys know what the base is for that one? 10. Okay? So there's one other thing you can do, which is you can write this as the log base B of 4 radical 3 over 9, let's say, divided by the log base B. And what you do is you put this base down here. And when I say B, you can choose any B you want. Okay? So for example, and this is called change of base. Again, you would have seen that in an algebra course. Change of base formula. So, for example, to show you how to calculate it, if you come over here and type in log of 4 times the square root of 3 divided by 9. Okay, so I could do that. And then divide by the log of 3. I get an answer. So I get this thing as 0.761. I changed to base 10 from base 3. All right, but you don't have to change to base 10. You can change to base E. So I could take the same thing I did before. I could say, all right, I don't want to do the log of this crazy mess. let me do the natural log of 4 radical 3 divided by 9. Enter. And divide by the natural log of 3. That's another way to get the exact same answer, 0.761. You can use any, you can change to any base you want. And if you just understand that natural log is base e, then I think you got it. Okay? Well, why do we care about natural log? Well, what did we say about e? E showed up last week. So e to the e to the x is its own derivative. That's one of the things that's really nice about it, right? Because e was the value that gave us a slope of 1 right at the point 0, 1 when we graphed it. So I guess I'm interested in how would we find the derivative of b to the x power? Okay? And let me start off with this one, this little fact. E to the ln x equals x. Now, how do I know that? Well, okay. So here's my question, I guess. Okay. So y equals the natural log of x is the inverse of y equals e to the x by definition. We just define it that way. We know e to the x is going to have an inverse. Let's call it the natural log. Okay, so the next question. Can we find the derivative? Because we want to be able to do calculus on this, not just algebra. Can we find the derivative of the natural log of x? Okay? And here's a little process we're going to use. We're going to start this way. E to the ln of x equals x. How do I know that? Well, because what do we say these things are? Inverses, right? And what does that mean? It means f of f inverse of x equals x. Does that make sense? Inverses mean they undo each other, right? If this thing is my f of x, then this thing is my f inverse. And so if I do e to the ln of x, what I'm really doing here, that's my f inverse of f of x. So it has to equal x.
How about x ln of e?
ln of e? The thing is that, right, I guess you could do, how would you do it the other way? If I did the natural log of e, that would be 1, okay? They undo each other. Or the natural log of e to the x would be x. That's the way to say it. They undo each other. Okay, but I want to start with this. And now I'm going to use something that we learned but haven't used in a while. We're going to use what's called implicit differentiation. Oh. Hey guys, the last time we were here, I took a derivative of e to the x and I showed you it was e to the x, and it took a while. We used this formula. Dun, 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 right? F of x plus h minus f of x over h. He does that here also. Derivatives of logarithms, and he comes up with the formula for the derivative. I guess I just don't want to waste your time. There's an easier way. Okay? So please understand that what I'm about to do here, you're not responsible for now, but you're going to be at the end of the semester, so why not show you? Okay? Implicit differentiation. It's a trick if you want. And the idea, the trick, is this. I'm going to take d dx of both sides. What does that mean, d dx?
The derivative in regards to x.
Derivative with respect to x. Yeah. So let me write it down. That's the key, is that I don't think we've ever really done both sides of an equation. All right, so here's what it says. d dx e to the ln x is equal to d dx of x. Does it make sense to you? I might be able to do that to both sides?
Yeah.
Okay. Well, what do you get on the right-hand side? What's the derivative of x? 1. Right? Now, what do you get on the left-hand side? What's the derivative of e to the natural log of x? Well, it's going to be e to the natural log of x, because we know that e is its own derivative, times, bong. Do you know what I'm going to write there? I need to take the derivative of what?
Natural log of that.
Of the natural log of x. The only problem is I never showed you how to do that yet. Right? But this might make sense to you. This is what I'm trying to come up with a formula for. The derivative of the natural log of x has to equal 1 divided by e to the ln x, if I just get it by itself, because this is a product here. Right? E to the ln x times the derivative of ln x is 1. And by the way, what is e to the natural log of x? We already said x. So what's the derivative of natural log going to be? 1 over x. And that's really nice.
How did you get 1 over x?
I
Can you
know.
explain that one more time?
Yeah, I'll try one more time. E to the ln x times the thing I'm looking for equals 1.
Not that.
So how do I get this thing I'm looking for? Here, what do I actually do to both sides? I divide by what?
I just didn't understand.
E to the
that
ln
E
x.
to the ln x equals x at the bottom there.
Oh, what did we start with?
E to the ln x. equals x.
We said that that's what they equal.
Oh, cool.
And why do we start that way? Again, because they're inverses. E and natural log are inverses. So if you ever have e to the ln x, that's the same as x. This is much quicker than trying to use the f of x plus h minus f of x over h. But regardless, I mean, we got our formula we need. We need that the derivative is 1 over x. And if I have that, I can do some practice problems now with you. So
So the derivative of the natural log of x is equal to 1 over x.
is equal to 1 over x. So now I'm going to give us 2 more problems to try. We want to find the derivative of each of these. Okay? So I have y is equal to the natural log of x squared plus 1. And then I also am going to show you f of x is, and this one is a little strange. That's why I thought it'd be a good example to show you. The natural log of x being squared like that. Okay. I mean, you have to understand something about the calculus in this chapter. In some ways, there's just not that much new stuff. You could argue that the only new fact I gave you so far today was this: that the derivative of natural log of x is 1 over x. You could argue that's the only thing new we've learned. Well, let's use that what we learned here. So if I want to find y prime and I know that my function is ln of x squared plus 1, you know what my derivative is going to be is 1 over x squared plus 1, because right? The derivative of the natural log of x is 1 over x, so the derivative of natural log of x squared plus 1 is 1 over x squared plus 1 times something. Bong. Do you know what I'm going to multiply it by? Why 2x? The chain rule. It's not new, right? It's the derivative of what was the inner function. Okay? So my final answer for this one, y prime of x is equal to 2x over x squared plus 1. Can I cancel the x's? No. What's the big thing that tells me I can't cancel the x's? That plus sign. All right? But this would be your derivative for the first problem.
Can we leave it how we had it up there, just times 2x though?
I guess, yeah. But I'd like you to understand that these are the same. Because how do you write 2x as a fraction?
2 over 1.
2x over 1, then multiply them, you get that. Okay? Here, let's try this one. F of x. I want to find f prime of x. I'll show you how I would do it. I'm looking this time at the outer function being the squared, right? So if it were me, I would write 2. That's my bing. ln of x, say, to the first power. Bing. What am I going to write next, guys?
Bong.
Yeah, what's the bong? 1 over x. And so I would say that f prime of x for this example would be 2 times the natural log of x all over x. Please don't try to cancel those x's. Then you'd be telling me I have no idea what natural log is. Okay? That's it. The natural log is a function that needs an input. You can't just write ln unless there's something after it. Okay? So this would be the derivative here. So on the homework, eventually this is what we're going to be doing our derivatives. This is really 2.4. But everything before it is kind of, I'm sorry, 4.4. Everything before it is kind of 4.2, just getting used to inverses and logarithms and things like that. Oh, one last thing to show you. This ties into Gina's question today. What about other bases? Other bases. See, here's a formula I didn't give you guys last time. So if you looked on the homework at that question Gina asked, you may have run into trouble. This gives you the more general formulas that you need. Well, I guess I gave you one of them. I thought maybe we'd figure out what the other formula is. Okay. So I think I would like to revisit that question. Which number was it, Gina? 33. And this is section 4.3. Now I'm ready. Let's go over it. So we're going to go ahead and use that formula there. It says the derivative of b to the x is equal to b to the x times the natural log of b. Okay. Let me try to use that formula with you. All right. So the function was 5 to the x power over 15 to the x power. So there's two different exponential functions that are being divided. Don't go canceling the 5 and the 15. It's going to get us in trouble. Okay? Can't do that here. But I guess what I can do is I can try and use the quotient rule to find my derivative, because it's a quotient. So I start off with ho d high. So I'm going to write ho is 15 to the x And now I need the derivative of 5 to the x. Well, this is where you need this rule that I didn't give you last time. But part of it was we hadn't covered logs yet. So what is the derivative of 5 to the x going to be?
5 to the x.
5 to the x
Natural log of 5.
times the natural log of 5. You just take the natural log of whatever the base is. Okay? Minus. See if you can do the top part, the next part. Hi de ho. So hi would be 5 to the x. And then I need the derivative of the denominator. So we get 15 to the x times the natural log of 15. All over, well, ho-ho would be 15 to the x squared. Okay? So now, let's see. I want to try and simplify a little bit. So one thing I could do is I could look for common factors. Do you see a common factor we could take out of the numerator?
15 and the 5 to that.
Yeah, I mean there's a 15 to the x in common. There's a 5 to the x in common. Right? So maybe I'll pull those out. So f prime of x.
Can you just cancel those or no?
Cancel where?
By making a huge math mistake. But 5 to the x minus 5 to the x on the numerator?
Well, I don't want to cancel, I want to factor it out. Okay? So when I cancel, when I factor out the 5 to the x and also factor out the 15 to the x, okay, what am I left with, I guess? That's the question. What's left in the numerator once you pull that out? Well, I have the natural log of 5 here minus what? Natural log of 15. You guys see that? So I have the natural log of 5 minus the natural log of 15. And down here, remember I had 15 to the x squared. So the next thing I notice is that I can cancel the 15 to the x in the top with the 15 to the x in the bottom. So now I have 5 to the x times the stuff in parentheses over 15 to the x. So it's funny because that's almost what I had before. I guess the only thing different is I'm going to have something up here now. By the way, is there a way to rewrite natural log of 5 minus natural log of 15? There's your log laws at work. So really, I guess we could say that f prime of x is also 5 to the x over 15 to the x, but you just have to multiply by a constant. So times the natural log of 1/3.
So
Okay.
Is that kind of is that a formula right there in itself almost?
Yeah.
I mean, anytime you have two constants raised to the x, you can just
Well, yeah, and it's
the natural log of those constants.
yeah, and actually there's an easier way. I should have seen that. Here. I know we wrote the problem the way we did because we wanted you to use the quotient rule. But what if you had had this problem, guys? F prime of x is 5/15 to the x power. Say f of x. Say that's my f. Let me call it f of x is 5/15 to the x power. Of course, 5/15, you wouldn't write that. What would you write? What would you write? 1/3. Okay. What's the derivative of 1/3 to the x power? It's 1/3 to the x power times what?
1.
Natural log of 1/3, right? It's always b to the x times natural log of b. So that's a faster way of coming up with the solution for this problem if you happen to notice it's the same thing. Okay, it's just using our new formula. And I mentioned there were two formulas. I guess I should make sure you guys know what goes here. What do you think the derivative of the log base b would be? We need that formula, right? So let me write that down. One final formula. The log base b of x. Say I want to take the derivative of that. Okay? Well, it's going to be 1 over x, but it's not going to be times the natural log of b. It's going to be divided by the natural log of b. Or maybe I'll write it times 1 over the natural log of b. How about that? I hope that makes sense to you. At least you have it. So now we can find the derivative of any exponential function. We can find the derivative of any log function. And using either this one formula in the oval or up above, I had a formula for you too. Hey, by the way, this is worth singing. You guys, what did we say the derivative of e to the x is? Could I say this? It's e to the x times the natural log of e?
Yeah.
Because what's the natural log of e? So it works. You multiply by the natural log of the base if you're taking the derivative of an exponential. You divide by the natural log of the base if you're taking the derivative of a logarithm. And I think with those things in mind, you ought to be able to do any of this stuff. Did you guys have other questions on the 4.3 homework? There was Gina's, but then wasn't there another one like that? Or any of the applications? Because I have time to do one of those if you want. What do you have, Rachel? 51? Geography. Yes. So they say f prime of x you wanted to determine. So yeah, I mean, now that you have the formula, it shouldn't be bad. F of x is 91,957 e to the negative 0.2x, right? 0 less than or equal to x less than or equal to 10. So x is the number of years since 2000, and f of x is the number of refugees that are annually coming into Germany. Okay. So it says, part A, determine f prime of x. F prime of x. Well, I'm going to write this 91,957 exactly like I did. The derivative of e to the whatever is e to the whatever. And then, bong, what do I need to multiply by?
Negative 0.2.
Why do we multiply by negative 0.2 here?
You have to take the derivative of negative 0.2x.
I need the derivative of what's up here, this exponent of negative 0.2x, right? I always, by the chain rule, need to take the derivative of what's inside. And inside in the exponential function really means up in the exponent. Okay. And, of course, the derivative of negative 0.2x is just negative 0.2. So I better multiply that out. See what I get. I have, let's see, 91,957 times negative 0.2. So it's going to be a negative derivative, right? F prime of, and what does that mean? The fact that it's a negative derivative, what does that mean? Yeah, something's decreasing, right? What are the units? That's important for interpret. A lot of you guys, if you got back that homework today, that 3.5 homework, and if you got a 2 at the top, it's because what I did was I checked the even problems. I know you guys checked the odds, but you didn't have the answers to the evens. And a lot of us struggled on the interpret part of this. That's why I have to emphasize, what are the units here?
People per year.
Sure, people is f of x per year, because we're talking about these 10 years. That's what x is. Okay? So now it says, for the next part,
Without the E.
use the derivative to determine the rate of change in asylum applicants. Oh yeah, I forgot the e, sorry. E to the negative 0.2x, people per year. So now, for part B, it says, hey, let's talk about 2002. So that's f prime of 2, right? That's what we need. So it's going to be negative 18,391.4 e to the negative 0.2 times 2 up in that exponent. Let me see if I can get that for you. So let's see. I have this thing. Oh, just lost it. I have this number times e to the, so I'll hit second natural log. That gives me e to the whatever. And now what I'll do is I'll put negative 0.2 times 2. Make sure that's all up in the exponent. And so I got negative 12,328. And so it was decreasing about 12,000 applicants per year in 2002. That's how I would interpret that. Does this make sense? Stephanie, all right?